Hi everyone. Today I will be talking about an important topic in linear algebra. It's about the inheritance of direct sum decomposition. So the basic model is the following. Let's give a fixed field F and a vector space V over F. So suppose that we are given a direct sum decomposition of the vector space V. For example, V equals V1 direct sum with V2. Then for which subspace W it inherits this decomposition. Say W also equals the direct sum of W intersect with V1, direct sum with W intersect with V2. So in the preceding exercise, we have seen this implication is not generally true. Okay, Wohan, do you have any counterexample about this?
Maybe we can choose W such that W intersects Vi are empties. For example, W be the diagonal and V1 be the x-axis and V2 be the y-axis.
Yeah, excellent. So Wohan just mentioned one basic example as follows. Let's take V to R2, okay, and V1 equals the linear span of the basic element E1, which is horizontal vector, and V2 equals the linear span of the vertical basic element. Then W is taken to be the linear span of E1 plus E2. Okay, that's great. So at least we have an easy counterexample of this inheritance. Okay. I want to mention here that you need to differ this case from that you may have seen in the set theoretic theory. Let's recall some basic result from set theoretic theory. So let S be a set with a union decomposition S equals S1 plus S2, and X is a subset of S. Then it is generally true that S equals the union of S1 intersect with X union with S2 intersect with X. Okay. This is sometimes called the distributive law of union and intersection. But in the category of linear spaces, as you've just seen, that this distribution law doesn't necessarily hold. Say, you may imagine as this set S as the set of basic elements of V, say alpha 1 alpha n. And S1 just equals the first k basic element. S2 just equals the last n minus k plus 1 basic element. Then so for example, if we take X to be a set X to be a subset of S, then we do not have this law. Say the span of X doesn't equal the span of S1 plus intersect with X plus span of S2 intersect with X. Since here we consider the linear span and the linear span of these two subset may be the only the zero vector. Okay. So this is different from the set theory. Okay. So one question is that for which there are some decomposition of the vector space, and for which subspace this inheritance relation holds. For example, in many practical cases, we consider the setting where V is a finite dimensional vector space and T is a linear transform on this vector space. Then we may restrict to the case where there are some decomposition are T invariant and these subspaces are T invariant. So for question is for which T invariant decomposition V1 equals V equals V1, there are some with V2, and which T invariant subspace W containing V, we have W equals V1 inside with W. There are some with V2 inside with W. Okay. So this is a basic problem we want to solve in this topic. Okay. So let me give you one possible approach of solving this problem. So, for example, now we have a nice we have a nice T invariant subspace, say W. W is given by some nice subspace related to our linear transformation T, and V1 and V2 are just arbitrary T invariant subspaces. Okay. For example, we may take W to be the kernel of T, or more generally, I just take W to be the kernel of any polynomial of this linear transformation T. Here, a polynomial is just a formal polynomial in one intermediate with coefficient in F. Okay. Now, in this case, we will prove that W has such an inheritance property. W inside with V1 or some with W inside with V2. And actually, to be concrete, we just write it as kernel of T equals kernel of T inside with V1. There are some with kernel of T inside with V2. Okay. And actually, one could even prove more that the first summand equals the kernel of Ft restricted to the subspace V1, and the same applies to the second one. Okay. So a single proof is as follows. So let us give alpha in the whole space, say V, yeah, and we explore the condition for alpha to lie in this subspace W equals kernel of Ft. For example, we assume that alpha equals alpha 1 plus alpha 2 in this decomposition. Then alpha lies in the kernel of ft, just equivalent to the statement that alpha 1 lies in the that's a bit slow. Ft of alpha 0. It just equals that ft alpha 1 plus ft of 2 is 0. But alpha 1 lies in V1, which is a T invariant subspace, and the same applies to V2. So this condition is equivalent to the ft f1 is 0 and ft f2 is 0. Okay, so it means that alpha 1 lies in the kernel of ft. And intersect with V1. And as you've seen, the kernel of ft intersect with invariant subspace is just the same as the kernel of this ft restricted to this subspace for the same reason. So the proof is complete. But now, similarly, one would imagine that the same inheritance property holds for the image of a kernel of ft. Okay, for some polynomial fx. And we would like to expect that the image of ft also equals image of ft intersect with v1, direct sum with the image of ft intersect with v2, and this also equals the image of ft restricted to v1, direct sum with ft restricted to v2. Okay, but the proof here is slightly non-trivial than the previous one. Okay, so again, let us take any vector in the space V and say alpha, for example, alpha lies in image of ft, which is the left-hand side of the equation. Okay, implies that alpha equals the ft or some beta. Okay, right? Okay, then we can write beta into a decomposition beta 1 plus beta 2. Say in v1 plus v2. Then our alpha equals ft beta 1 plus ft beta 2. So it lies in the image of ft restricted to v1 plus direct sum with the image of ft restricted to v2. And of course, this set lies in image of ft intersect with v1, direct sum with the image of ft intersect with v2. So at least we prove that, okay, and all of these lies in image of ft, certainly. So we prove this identity since alpha from the right hand side lies in ft, and from the left hand they are in image of ft, and on the right hand they also equal image of ft. So all the inclusion in this chain must be equal. Okay. But here I would like to give you a warning. So I mean this inclusion is not so automatic. In the sense that, okay, I will give you a question here. Okay. That's right. Maybe question prime. Okay, just a little question. So for subspace, say W inside V, is it generally true that for any polynomial fx, it holds that the image of ft restricted to W equals the image of ft intersect with W? Okay. So you may see if we replace image by kernel, then this equality of course holds. But it is not the case when we consider the image. So I would like to give you a quick counterexample. Of course, we talk about T-invariant subspaces. For example, we just take V, still in R2, and W to be the vector space spanned by E1, okay, and our linear transformation has a matrix representation that is strictly upper triangular one. Okay. Then it is okay, and we just take fx to be x. Okay. It is clearly seen here that image of T restricted to W is 0. Since W lies in the kernel of T. But the image of T intersect with W is just a W. Since clearly the image of T is equal to W. So this gives a strict inclusion here. So this is what I'm going to say about this inclusion. It's not so automatic as you may have seen. The important observation is the following. When does this property hold for T-invariant subspace W? Okay. We call this property as star. Okay. T-invariant subspace W satisfies star. Actually, if and only if W admits a T-invariant direct sum complementary. It just means that there exists another T-invariant subspace U such that the direct sum of W and U equals V. So it is really the case we met here, but it's not. But here, in this counterexample, W doesn't admit a T-invariant complementary. Okay. This observation is non-trivial, highly non-trivial, and the reference I would like to provide is the textbook of Hoffman and Gans. I wish I put it clear. So, just now we consider the case when the subspace W is good and our decomposition is somewhat arbitrary. And now I would like to give you another possible approach where the decomposition is good in some sense, but the subspace W is just an t-invariant one. Okay. So maybe here equals V1 and V2 is nice. And W is just an invariant. For example, we have seen many nice decompositions of this vector space according to the linear transformation T. A source is that, for example, V is from the primary decomposition of V. Okay, let's say that V can, our vector space V can be decomposed into a direct sum of t-invariant subspaces of Vi, just in the same manner that the characteristic polynomial of the linear transformation, say ft, or we just consider its minimal polynomial, is composed into the product of powers of its reducible factors. If, for example, we write PIX, the power di here, or we just write of PIX to the power r. Here we just take Vi to be the kernel of PIX to the power di, which also equals the kernel of PIX to the power r. So from the primary decomposition, we have already seen vector space, which is decomposed into a direct sum of nice subspaces given by some kernel of its factors of this minimal polynomial. So in this sense, we would like to consider the following case. So let's put it to be simple. That V is written as a direct direct sum of kernel of ft, direct sum with kernel of gt, and that W. Then I claim that for any t-invariant subspace W must inherit this primary decomposition. And W equals W intersect with kernel of ft. There are some with W intersect with kernel of gt. So I to give you a single proof of this fact. For example, let me call you some basic facts about such a decomposition. Okay. Say, if we are given two polynomials f and g, then the kernel of the greatest common divisor of f and g of t, okay, thus equals the intersection of kernel of ft and kernel of gt. And the least common multiplier of f and g and t is kernel, thus equals the kernel of ft plus kernel of gt. These are two easy identities that have occurred in your exercises. Okay. So from this and our condition, we may deduce that we know the intersection is trivial, which means that let us write t as the greatest common divisor of f and g. This has zero kernel, which means that dt is injected, right? And if we write ht to be the least common multiplier of ft and gt, then the kernel of ht is just a whole space, which means that ht is 0. And in particular, we see that ft composed with gt is 0. Okay. Since the product of f and g is the multiple of h. Okay. So our task is to write an arbitrary vector in W as two vectors. One lies in the intersection with W and kernel of ft, and another lies in the intersection with the intersection of W with gt. Okay. So where does the decomposition come from? We would like to use the property from this greatest common divisor. Okay. For that, we have this Bayes' theorem that the greatest common divisor can be written as the linear transformation of f and g. Say there exists u f v which is polynomial such that d of x, say d of t equals ut of ft composed with ft plus vt composed with gt. Now we will use the property that dt is injective. So injective just means that we can view dt, roughly speaking, as the identity. And then for any alpha in W, alpha equals dt inverse decomposed with dt acting on alpha. And now we expand dt using this Bayes' theorem as dt inverse composed with ut ft alpha plus vt gt alpha. Okay. Now alpha has a decomposition where the first let's write alpha 1 will be dt inverse vt gt alpha. It lies in the kernel of ft. Okay. Since all these polynomials about t commute with each other, and f composed with g is 0. Okay. And we may take alpha 2 will be dt inverse composed with ut ft alpha. And this lies in the kernel of gt. So the proof is completed here. Quite a nice but short proof. Okay. Do you have any question about this?
Why is W invariant under T inverse?
Okay. Oh, here we actually use this property. Okay. Let me explain more. Yeah. Now, W is T invariant, so of course W is invariant under dt, which is a polynomial of T. Then, since dt is injective, then just map W itself, W to itself, and this map is subjective due to the dimension reasons. If we decompose the equality with dt inverse on both sides, we will get W equals dt inverse on W. Okay. Now this proves that W is also invariant on the dt inverse.
Okay, thanks.
Okay. Nice question. So we have seen these two possible approaches about the inheritance of direct sum decomposition. Okay. Now, let me give you a final exercise about this topic. And I wish this exercise to be helpful for you to understand this topic. Okay. Okay, I will write this as a query. So for you, this is an exercise. Okay, so that's the minimum polynomial of t, let's say mtx equals the product of x minus ci to the power I. Okay, this decomposition holds over the field of complex numbers, where ci is complex and I are natural numbers. Then, for any polynomials ft and gt, fx and gx, the kernel of ft is contained in the kernel of gt if and only if for any I from 1 to k, the minimum of ei I is less or equal to the minimum of fi I, where ei, fi are multiplicities of the root ci in the decomposition of fx and gx. We simply solve this exercise using our previous discussions about this inheritance of direct sum decomposition. Okay, that's all. Thank you for listening.